Students, hi, this is Mr. Bob. In this video, I'm going to walk you through a particular application of electromagnetism and magnetic fields that's really interesting, really useful, both historically and in present day. And so as the handout suggests, if you are able to print this handout, that might be helpful to you. You can just kind of write on it. If not, it's not a big deal. You can just scribble down these X's on your own piece of paper and we'll walk through it together. So remember, we've been talking about electromagnetism and right-hand rule and things like that. And we're going to apply those things here to kind of get at what's going on here. So here's the setup. And oh, the other thing I wanted to say is you probably want to have several different colors. Ideally, it works best if you have 3 different colors available to you, either via colored pencils or different colored inks. Up to you. Okay, so here's the scenario. We have this charged particle and it's traveling to the right with a velocity v, and it enters this uniform magnetic field of strength B. And notice by the X's that are shown there, that means the magnetic field strength is headed into the page, right? And then we're going to just follow through and answer a series of questions, and we're going to walk through it together. So question A down here says, assume the charged particle is a proton. Okay, it's a proton, so it has a positive charge. A1 says, draw the force vector the particle feels upon entering the magnetic field. So let's do that together. So notice I'm going to advance the particle to this spot right here when it first enters the magnetic field. And let's go ahead and do the right-hand rule together. If it's moving to the right, I'm going to put my thumb in the direction to the right, and the magnetic field lines are into the page. So in what direction is the palm of my hand facing? Palm of my hand is facing up. So that means it's going to feel a magnetic force in the upward direction. So I'm going to put a key over here because I don't want to do this. So magnetic force is going to be indicated by basically these red arrows that I'm going to draw. So at this point, when it first enters the magnetic field, this positively charged particle is going to feel a force in the upward direction, like so. Okay. So what's the particle going to do? Now we learned previously, right? The other big assumption we want to make here is that the magnetic force is the only force acting on the particle in this scenario. So in other words, gravity is so weak, or we're looking at it from above, that gravity is insignificant. Okay, so if this is the only force acting on this particle, then it's also the net force on the particle. And if it's the net force, remember, that particle is going to feel an acceleration in that direction. So in other words, if a particle is traveling to the right and all of a sudden it feels a force in the upward direction, what's it going to do? It's going to start curving. So notice, it might look something like this a few moments later, right? It has moved upwards, so to speak, because the net force is causing it to move in that direction. But let's go ahead and apply the right-hand rule again with a particle in this spot. So at this point, the speed of the particle is now in this direction. Let me see if I can get this kind of right. Yep. So now we have a v that's like right here. So if I do this now, the v is kind of headed up and to the right. My fingers are still pointing into the page. Notice my hand is now still pointing up. It's like up and to the left. So that means the magnetic force is now going to be in this direction, like so, something like that. Okay. All right. And so what's the particle going to do? Well, it's going to feel a force. If it feels a net force in that direction, it's going to kind of keep curving. So it's going to probably move something like so, right? And, we can debate how much, and I don't give you numbers, but you can know qualitatively what's going on here. So notice I'm going to actually advance it a little bit further until like right here, let's say. And I'm going to apply the right-hand rule one more time. So at this point, I'm going to say this particle is moving like this. Okay, this is the V. And so if I apply the right-hand rule now, thumb is now pointed straight up, fingers into the page. I feel a force to the left. So notice the magnetic force is now here. And let me just add this one in here. It would be something like that. Now, what do you notice? What do you notice is going on with this particle's motion? Notice all these force vectors are pointing towards one common point, roughly speaking. And that's because this particle is moving in a circle, okay? So this gets to question part B, right? What is the particle doing? It is moving, and I'm just going to kind of use dotted lines here to to show it, but this particle is going to move in some sort of circular motion. Okay, so we can say here, what's special is that the particle is moving in a circle, and not just any circle, but it's a special kind of circular motion. Here's what I want you to think about. Notice how the force is always directed at a right angle to the current direction of the particle, right? Because just by QVB sine theta, right, the magnetic force is always directed at a right angle to the speed of the particle, to the direction of the velocity. So if that's the case, then the particle is never speeding up nor slowing down. It's just changing direction. Let me say that again. Because the magnetic force is always directed at a right angle to the direction of the velocity of the particle, all the magnetic force can do is change a particle's direction. It can't make a particle in and of itself, by itself, speed up or slow down. So if that's the case, if you recall, something that's moving in a circle but not changing speed is a special kind of motion, okay? And it's actually called uniform circular motion. So let's just write that down, uniform circular motion. And we have this abbreviation you'll see sometimes. I'm going to use it here, UCM. So the particle is moving in a circle and maintains a constant speed. This is called uniform circular motion. Okay, so now that should ring bells off in your head because we have studied uniform circular motion. Remember the flying pig and things like that? Uniform circular motion, there are equations in section 6.1 that we're going to use to help analyze the situation. Okay, so part C says, using only symbols, no numbers, derive an expression for the radius of the particle in terms of the variables already identified in the additional quantities shown below. Again, assume gravity is not a factor. Okay, so let's talk through this. So we know already from subtopic 5.4, we have this equation, which basically says that the force, the magnetic force exerted on that particle is Q V B sine theta. And I also just mentioned that theta equals 90 degrees, okay? And so that means sine of 90 is 1. So I can just simplify this to say, for this problem, the force is QVB. Okay, the other thing we know, if we go back to uniform circular motion, which is section 6.1 in your data booklet, I'm on page 7 of your data booklet, is that the acceleration of such a particle moving with uniform circular motion is equal to the speed squared divided by the radius of the circle it's traveling in. And the third thing we need to remember is our trusty old Newton's laws, right? And again, you shouldn't have to refer to this, but subtopic 2.2 tells you that the net force acting on an object equals the object's mass times its acceleration. Okay, so now watch what we're going to do here. I can basically say, oh, look, acceleration in this case, in this special case, is equal to v squared over r, right? So let me put that in there. When I do that, I get that the net force is equal to mass times the speed squared of the particle divided by its radius. And we already established the fact that the net force is equal to the magnetic force because the magnetic force is the only force acting on the particle. So we can say that F sub B equals F net. Therefore, F sub B equals mv squared over r, but we already know that the magnetic force is equal to QVB. So this means that I can set, let me be really explicit about this, I can set this in over here, right? So I'm going to go this way with it. I'm going to say QVB equals mv squared over r. Now, what are we trying to solve for? We're trying to solve for the radius. Oh, and look here in the problem statement, it tells me to use a capital Q and a capital M. So I'm going to do that here in the next step. So I'm just going to kind of go down here, sideways a little bit. And I'm going to say, I'm going to do a couple things at once. I'm going to put the Q and the M, and I'm going to bring the R. The R is going to come over here to the left side of the equation. I'm going to multiply both sides. Let me just do a couple things here. Let me multiply by R over QB. Yeah, that'll do it. Okay. And in doing so, what happens, right? These R's cancel. The B and the Q cancel with this one. So what am I left with? my final result is going to be that R is on this side. And you also know that one of the V's cancels here with one of these V's. So I'm left with the V over there. So R equals MV over QB. And let me actually, again, take one more step here. R equals capital M, V over capital Q times B. Okay, so this is kind of the answer to part C here. So let's pause here. This is a really important result. If I want to know what impacts the radius of the travel of a charged particle through a magnetic field, there are 4 things it depends on, right? It depends on the speed of the particle with which it enters, depends on the strength of the magnetic field. Those are 2 important factors, but the 2 most important factors for our purposes here are the 2 that I haven't mentioned yet. That the mass of the particle impacts the radius, and the charge of the particle impacts the radius, okay? And not only does, well, yeah, I'm just going to stop there for now. So what I want to say, and this is really key, note that the mass, the particle mass and particle charge impacts the radius. Okay, and you're going to see why that is key in a second here. So let me just kind of put that over there. Okay, so part D says if instead of a proton, the particle was now a deuterium nucleus. Remember, deuterium nucleus is the same as a proton, except for it has a neutron, right? So how would your answers to parts A through C change? So let's see here. Let me use this result. I'm going to use a different color. I'm going to use, let me use green. Is that green? No, that's green. Okay. So R equals MVQ over B. So let's think of this. If I don't change the magnetic field, that's the same. I'm not changing the charge of the particle, right? Because a proton does not have a charge, so Q hasn't changed. I haven't changed the speed of the particle. What has changed? If I have 1 proton and 1 neutron, the mass of the particle has gone up, right? If the mass of the particle has gone up, then what's going to happen? The radius for deuterium is going to go up, or it's going to be more than the radius for that of the proton from the earlier example. You can think about it this way. If you're a car turning around a corner, right, a more massive car is going to take more massive vehicle is going to take a wider radius, all other things being equal, to make that turn as compared to a lighter vehicle. So that's another analogy you might want to use. So if I were to come up here and do this, let me kind of go back up here to the top now. So deuterium, right? Deuterium is going to have the same thing. If I apply the right-hand rule to at the same spots, I'm going to get the same idea, but they're going to be smaller. They're going to be the same size force vectors, but the resulting sort of travel is not going to be as dramatic because, again, it's a more massive particle. So I'm going to, in green here, draw what deuterium would look like, and that might look something like so. Okay. So let me just be clear. Let me just go back here. The proton might look something like this. Okay. The deuterium, so this is the proton. This is the deuterium. So what can we say? The answers to part A through C, we can say the radius would be larger for deuterium. Okay, let's go to part E. Part E asks you to look at this again, and now it says, if instead of a proton, the particle was now an electron, how would your answers to part A through C change? Be sure to sketch the path of the electron. Okay, an electron. Let's go back. Remember right-hand rule. If this is an electron, I'm going to use gray for an electron. Okay, here's the electron. At the entrance here, right? Velocity to the right, fingers going into the page because that's where the magnetic field is. Positively charged particle is going to feel a force up. Electron is negatively charged, so it's going to feel a force down. Right, so the electron is going to feel forces in this direction, and it's going to curve, and it's actually going to curve more strongly, right? More it's going to make a bigger, not a bigger curve, it's a tighter curve, right? Because it's a lot less massive. And this is not by any means drawn to scale, but it's going to look something like this maybe, okay? Because it's a lot less massive than the proton, and certainly a lot less massive than deuterium. So this would be the electron. But what is the same is it's still circular in nature. It's still uniform circular motion, okay? So what do you get here? What we could say is R equals mvq over b over qb. The charge is the same, the magnetic field is the same, but the mass is a lot lower. And no, it's the opposite direction. So we can say electron will curve in the opposite direction and with a smaller radius. Okay, so now look at what we have here. This is just amazing. Notice, let me put little arrows on here. Notice what we have here. We have here a device, an apparatus, that where we can send a sample of stuff. And if we don't know what that sample has in it, right, we can send it through this magnetic field. And then what's going to happen? Just naturally, if I just tweak things just right, the magnetic field strength, the speed of the particle that's entering, and I can do those things. There are ways that you can do that. I'm not going to talk about in this video. Then I can basically set up detectors. I can set up detectors over here. Let's just say I have a whole bunch of detectors over here. And I have a whole bunch of detectors over here. And in fact, I could even put detectors over here, because what's going to happen, some particles might not be charged at all. And if they're not charged, they're going to go through the magnetic field undisturbed, so to speak, in terms of their path. And so notice what I have here. I have a device where I can figure out what is in a sample. I can say, oh, this sample has a lot. If I see a lot of detections here, I can say, oh, wow, this sample has a lot of protons. If I see a lot of detections here, I can say, wow, this sample has a lot of deuterium isotopes, et cetera, et cetera. You get the idea, right? And so this device has incredible applications. One could say massive, massive applications. Get the joke? Because you can discriminate. You can basically figure out things that have different mass, things that have different charge. You can be very finely, a fine sort of distribution of what's going on. And so a couple of uses for this. If you recall, when we were talking about particle physics, you listened to the podcast about what's the antimatter, about the idea that the electron has a cousin called the positron, right? It's this antimatter pair. How did we discover that originally? Because in that cloud chamber, scientists noticed that while the proton was curling in one direction, they saw another particle, excuse me, not the proton, while they saw the electron curling in one direction, they saw another particle with the same curl, because it has the same mass and the same charge, but in the opposite direction, right? So if you see something like that, then you realize, whoa, that's got to be, the exact cousin. It's got all the same characteristics as the particle that you were looking for, but it's got an opposite charge. So the positron was discovered this way, using a device like this. Also, something that's been in the news lately, the muon. The muon is, remember, the heavy cousin to the electron. It's about 200 times more massive than the electron. And the muon was originally discovered with this because, again, you would have a detector here, and because the muon is more massive, it could have taken a path something like out here, right, down to another spot in the detector, and scientists would have been like, whoa, what's going on with that? And that's what happened way back in, I think, the mid 1930s. So discovery of different types of particles, quantities of different types of particles, that's happening all the time. Okay, this is also happening at the CERN, by the way, at the Large Hadron Collider. This is one of those devices for sure that they're using. And then the one thing that I want to make sure you understand is this has huge applications, not only in physics, but also in chemistry. So maybe some of you have studied chemistry, you've come across this before, but this is what's called a mass spectrometer, right? You can take a sample, a chemistry sample, and figure out how much of different elements you have and how much of certain isotopes you have based on sending it through an ionization chamber, which causes that sample to be ionized. And then once you do that, you can select for a certain velocity. It's called a velocity selector. And then you can send it through here and get a sense for what it has. I will tell you in my past, when I was on the submarine, we had a device that would analyze the air sample, take continuous air samples of what we were breathing, right? And that was really important to figure out how much oxygen, carbon monoxide, et cetera, nitrogen was in the air on the submarine. And based on the results that device was displaying, technicians would make adjustments to basically how much how much different components of air were being added to the submarine's atmosphere. So I could go on and on about this, but this is an incredibly useful, important application of some of the ideas we've been using, namely electromagnetism, right-hand rule, going back to circular motion, and obviously Newton's laws. Okay, I hope you've enjoyed this video, and thank you very much for watching.